Okay, here we go. Part 2 of my 3-part series on trig graph transformations. If you haven't watched the first part, I would definitely watch that first because I really dive into, where these A values and B values and C values and D values are all coming from, what they mean. But just really quickly, the A value is giving you your amplitude or your height. Your B value is all about your period. Your C value is all about your phase shift. And your D value is your vertical translation. If you want more detail on all that stuff, please go back to part 1 and check it out. I also put a pretty cool little Geogebra video online as well. I made this app that basically graphs all 6 trig functions, and you have the ability to use a slider to change the A value, the B value, the C value, and the D value, and see what effect that has on the graph. So check that out as well. In this graph right here, we have no difference in our amplitude. Our amplitude is still 1. We have a B value of 2, so that means our period, the period formula for sine is normally 2 pi, but let's divide that by B. All right, for sine and cosine, and their reciprocals, it's 2 pi over B, so 2 pi over 2, so the period now is pi. So this graph is going to finish one cycle in half the length of the original sine, of the normal sine. The everything else stays the same, so I'm going to still bring it up to +1, down -1. If this is pi, then this is pi over 2, this is 3 pi over 2, and this is 2 pi. The normal sine goes up to here, down to here, down to here, and up to here. That's the normal sine. That's when the period is 2 pi. Remember, the period is how long it takes for the graph to complete one cycle. Yeah, so this is the normal sine. Goes up to 1, down to -1. It's a little sloppy, but what happens here is the period gets cut in half. So now the graph starts and ends in half the distance. Alright, so you can see a nice comparison between the two. So now our period is just pi. So pi over 2 now becomes our x-intercept. Pi is an x-intercept, and 0 is still an x-intercept. Our maximum still goes up to 1, but now it's pi over 4, comma 1. Pi over 4 being right there, 3 pi over 4 being right there. So 3 pi over 4, comma -1. So the domain is all real numbers. The range is the same as it normally is. X-intercepts 0, pi over 2, and pi. Maximum I just said, minimum I just said, no asymptotes, no phase shift, no vertical shift, and no reflection. So let's move on. All right, next up, in this one we have a value in front, which is our A value. It's an amplitude of 2. So that means this graph's going to be twice as tall as the original. And we also have a D value of 1. So we have a vertical translation up 1. Alright, so let's graph quickly the original cosine, just to get a general idea of what this thing looks like. So I go down here, and notice I'm graphing it with a y-axis scaling that's a little bit squished, because when I amplify the function, I make it twice as big. That means I'm going to bring it up to here and down to here and up to here. I'm not going to change the x-intercepts though. So nothing changes about this except the height. And that's not a great looking graph. X-intercepts stay the same, something like that. That's what happens when we change the amplitude. It goes from 1 to 2. So this point goes down here to -2. This point goes up to positive 2. This point goes up to positive 2. But there's also an upshift, a vertical shift of positive 1. So I need to take this whole thing and I need to move it up here. And this whole thing needs to go up here too. Something like that. All right, it's not perfect, but it's pretty darn close. This might need to go up a little bit more. That's pretty good. So now let me get rid of that. So now I'm all the way up to positive 3. This is positive 2. And I can see here that it still has the same period. The period hasn't changed. It just became twice as tall and it moved up 1. The whole thing shifted up 1. So this is still pi. This is pi over 2. And this is 3 pi over 2. Those haven't changed. The maximum value here, of course, is 0, 3. And here is 2 pi, comma 3. So we'll put that here, 0, 3, and 2 pi, comma 3. The minimum value is down here at pi, negative 1. In other words, when we plug in pi for x, we get negative 1. 2 times cosine of pi plus 1. Well, cosine of pi is negative 1, so 2 times negative 1 plus 1. Negative 2 plus 1 is negative 1. There it is. Pi, comma, negative 1. Alright. Let's see. Domain, of course, is everything. This thing will just keep repeating itself over and over again. The range, that changes pretty drastically. It goes from negative 1 to positive 3 inclusive. X-intercepts are a little bit challenging. It doesn't look like they're super clear to see. It's definitely not pi over 2. So let's calculate this. Let's take the function. Let's take the actual function 2 cosine x plus 1, and we'll see where it's 0. So you just set it equal to 0. So 2 cosine x is equal to negative 1. Cosine x is equal to negative 1/2. I'm getting that trig function by itself. So where is the cosine negative 1/2? What angle? Well, let's see. Whenever I'm confused about this, I always go back to my special angles, all my reference angles that I have memorized. Alright, sine of 0 is 0. This is 1/2. Radical 2 over 2. Radical 3 over 2. Radical 4 over 2. Radical 4 over 2. Radical 3 over 2. Radical 2 over 2. Radical 1 over 2. And radical 0 over 2. Alright, so I have that sort of pattern memorized. The cosine of pi over 3 is 1/2, but I want to know where it's negative 1/2. So I know it's going to have something to do with pi over 3. So let's draw a little reference right down here. All students take calculus. So cosine is negative in these two quadrants. So I need a quadrant 2 angle, that has pi over 3 as its reference angle. So pi over 3 is about 60 degrees, so it's going to look something like this. So if that's the reference angle, the actual angle, the second quadrant angle, is going to be 180 minus that, or pi minus that. So pi minus pi over 3. Well, that's 2 pi over 3. So there's my first answer. This dot right here is 2 pi over 3. Where's this one? Well, that's going to be the quadrant 4 value. So the x-intercepts is 2 pi over 3, comma 0, and something, comma 0. So I need the quadrant 4 equivalent, to pi over 3. In other words, if this is our reference angle, remember our reference angle is always the angle between the x-axis and the terminal side. I want to know what this whole angle is. That whole angle. Well, it's going to be pi plus pi over 3. So what's pi plus pi over 3? That's 4 pi over 3. So that's my second x-intercept. There you go. no asymptotes, and no phase shifts, no reflections. This one just had a vertical shift of up 1 and an amplitude change +2. So again, everything kind of keeps coming back to all these, the unit circle and sine and cosine values and your special angles and all this stuff, right? It all keeps resurfacing, so it's obviously important. You need to know how to work with these different quadrants and figure out these values. You can also just throw this into a calculator and you'll come out with a decimal value, and if you can figure out that that decimal value is 2π/3, you're in good shape. Okay, next up. Tangent. Here we have a rational a value. It's 1/4, so that's our a value. And we have a phase shift right pi units. Okay, so the tangent normally looks like this, right? But now it's going to be kind of squished down. It's going to be kind of squished down, something like this. And it's also going to be moved to the right pi units. So it's going to be over here, kind of squished down. So that's the general idea here. Let's get some actual values though. The period of this thing is still pi units. That's what it normally is. So let's see, if I know that 0, 0 is usually a point, I want to move right pi units. So I'll say that this is pi right here. This is pi/2. This is 3 pi, well, it's a little off. This is 3 pi/2. And this is 2 pi. So now I'm moving right pi units. So now there is my first point. That's 0. And if the period is pi, that means that that's how long it takes to repeat itself left and right. So I need to go half of that this way and half of that this way. And those will be my asymptotes. So this is my left-hand asymptote. Try to draw it as straight as I can. It's a little hard. And this is my right-hand asymptote. So right there, the difference between 3 pi/2 and pi/2 is 1 pi. This distance is 1 pi unit. Okay. So let's see. This would be pi/4. This would be 3 pi/4, and this would be 5 pi/4. 3 pi/4. I need to figure out that key value. Remember what I said last video? Tangent has 3 key values. So if I plug in 3 pi/4, what does that value give me? Well, 3 pi/4 minus pi/4, or minus pi rather, I'll change that to 4 pi/4. So that's negative pi/4. So I need to know the tangent of negative pi/4. Well, the tangent of pi/4 is 1, so this ought to be negative 1. So 1/4 times negative 1 is negative 1/4. So when x is 3 pi/4, y is negative 1. So I'll put that right down here. Or negative 1/4 rather, sorry. So let me do that again. When x is 3 pi/4, y is negative 1/4. Multiply these two together. So let me zoom in on this. Right? I could make this negative 1/4 right there, assuming I keep this as negative 1. But I might not want to do that just because it's so kind of cramped. It's totally up to you though. What I might do is scale my y-axis so that this is negative 1/4, this is negative 1/2, this is negative 3/4. So this is going to be negative 1 right here. It's kind of a funny way to scale it. Maybe I'll do it a little differently actually. Maybe I'll do it so this is, and this is really just all about preference. I don't want to make my graph seem too squished. So maybe I'll say that this is, yeah, actually I think I like that. This is negative 1. This is negative 1/2. This is negative 1/4. I think that's fine. I'll keep it that way. So this is a half, this is 1, so this is a fourth right here. Alright, so my point when I plug in 3 pi over 4, I get negative 1/4, which is right here. I'm put in red so it's easy to see. So this is a point, and then if I plug in 5 pi over 4, which is this x value, so if I go up here and I plug in 5 pi over 4, let's see what happens. Should be pretty simple. 5 pi over 4 minus pi, well that's just pi over 4. The tangent of pi over 4 is 1. 1/4 times 1 is 1/4. So that's going to be right here. And I'll put it in red again. So again, tangent has those 3 key points that I want you to look at every time. Let's just graph it. Alright, there it is. Alright, and the normal tangent graph would look, it would go all the way up to here. If it were shifted right pi units, it would go up to here. So you can see the difference between the normal tangent graph and the squished down version of it. Amplitude, there isn't any. Even though the a value is 1/4, that doesn't change the amplitude of the tangent, because the tangent doesn't have an amplitude in the first place. It does squish it down though. So if you want to put that a little bit, if you want to put that kind of like in a parenthetical, it squished by a factor of 1/4, something like that. That would be fine. The domain, well, the domain value is all real numbers, all x values, except, let me erase this, except when the asymptotes occur, which is at pi over 2, and then every pi units thereafter. So every pi times n, if n's an integer. If n's an integer and you multiply it by pi and you add that to where it starts, you're going to get an asymptote. So pi over 2 is the first asymptote. Every asymptote thereafter, whether it's this way or whether it's this way, is going to be a multiple of the period times n being an integer. The range is everything. X-intercepts pi comma 0, maximums, minimums, none of those. Asymptotes, x equals pi over 2, x equals 3 pi over 2, and then they would of course go on forever. I'm not going to write all of them though. Phase shift, yes there is a phase shift, it's right pi units, and a vertical shift, nope, none of that, and no reflections. So there you go. 3 more, part 2 of my trig transformation series. In the next one I'm going to be tackling some of the reciprocal functions, a little bit more complicated stuff, so look forward to that.